Hello, welcome to Material Science lecture. So this is module 4, lesson 1. So in this topic, we're going to cover topics of dislocation and plastic deformation. So primarily, we will look into metallic materials. So in this lesson, we are going to see how atomic bonding, crystal structure, the different crystal structure in metals, and also the edge and screw dislocation or just line defect is going to affect the material properties or the inherent properties of materials, especially its deformability. So let's get started. So by the end of this lecture, you should be able to elaborate the differences between elastic and plastic deformation. So this is basically just a revision from mechanics of solid. So what are the differences between elastic and plastic deformation? You should be able to elaborate that by the end of this lesson. And you should be able to explain the dislocation effects, how dislocation affect ductility of materials, and also you should be able to explain what is slip system in crystalline solid. So as I have mentioned that we are going to just talk about deformation in metallic materials. So deformability of metallic materials. So metal, if we compare to other materials, have relatively good deformability. So what is deformability? It is the ability of the materials to be deformed. So I have a piece of paper clip that I try to straighten. So what's going to happen is if I load them and then I unload them, and I repeatedly do that, twist and untwist them, they still are not breaking into two. So this is because of the atomic bonding inside these materials. However, with ceramic, for instance, if I have a piece of glass and I try to bend them, I might take a little bit more force, applied force to bend them, but as soon as they start to bend, crack will happen straight away. So you will shatter that materials straight away. So this is because of the different bonding that form inside these two materials. So for ceramic crystal, for instance, it is formed by ionic bonding. So this structure consists of positively charged ion and a negatively charged ion. So the bonding happens when these two meet each other. So they interact with each other. So when you try to bend them, this is going to slide. The positively charged ion is going to slide and they're going to meet a similar charged ion. So the repulsive force between the two identical ions will shatter these materials. So this is what happened. This is why ceramic materials are brittle. However, with metallic bonding, the bonding inside the materials are all identical throughout the entire atomic structure. So when atomic series are displaced, basically there are no changes in the atomic structure. So thanks to metallic bonding, metals have good deformability. So basically the ions can just slide on top of each other. So good deformability is the basis for many manufacturing process. So we want metal, why metal has been used in a lot of engineering structure? Because it has good deformability. You can easily bend them, you can draw them, or you can roll them or forge them, and they can easily be deformed to whatever shape you want them. However, their level of deformability are not all the same. So depending on their crystal structure, they will have different deformability. And this is what we're going to cover in this topic. So before we move further in discussing about what happened during deformation, that makes metallic materials have different level of deformability, I would like to revise the topic, the two types of deformation that you have learned during the subject mechanics of solid. So we know that any materials can deform elastically or they can deform plastically. And here I would like to talk about what actually happened during elastic deformation and during plastic deformation. What happened to the atomic arrangement? So what is elastic deformation? So elastic deformation is a temporary shape change that can be reversed after the force is being removed. So that the original, when we remove the applied force, it can change back to its original shape. So just like a rubber band, when we stretch them, it will elongate, and after that we release them, they go back to their original position. So the applied force is not enough to change this structure of these materials. So it is still working in its elastic region. So what happened during this elastic deformation? What happened to the atomic bonding? So what happened during elastic deformation? So during elastic deformation, as we have learned before, atomic metallic materials has all its atom in a repeating order throughout its volume. So it has its crystal structure, which is the BCC, FCC, and also HCP. And all of these atoms are bonded together with metallic bonding. So elastic deformation involves stretching of this atomic bonding, so causing separation between the atoms. So when we try to separate them, what's going to happen is there's going to be a restoring force act to return the atom back to the equilibrium position. So if the force is not high enough, this atomic bonding, the stretch of the atomic bonding, can be restored back to their equilibrium position. So if you look at this diagram here, when we put a force during elastic deformation, all the atomic bonding will stretch. But when we restore, when we take that applied force away, what's going to happen is they're going to go back to their original position. So for structural member, in structural application, in civil application or engine design, we are always going to keep that our application for structural member to be in elastic region. For instance, I have this model of this truck here. So all structural member in this design, when the designer design them, they will calculate all the force that is enough that can be applied to the structural member. For instance, this two force member here, they will calculate that it will be just in a safety where these materials will only can deform in elastic region. So for structural member, we are going to keep these materials, any materials, to be in just their elastic deformation region. So during elastic deformation, atoms do not slip past each other. When they start to slip past each other, it is what we call as plastic deformation. And now they can change their shape. So because plastic deformation involves the slip of the atoms, so atoms now are not in their original position anymore. So this is a permanent deformation. If we have stretched, let's say, this elastic band beyond the elastic region, permanent deformation can happen to these materials. It's the same with this structural member as well. If we put load too much, what is going to happen? They will start to stretch beyond the elastic region, and you can see a permanent deformation happen to that materials. That's why I said for structural member, we normally will keep our applied load in a safety region where it is only going to cause elastic deformation. So plastic deformation is a permanent deformation. So the deformed materials does not return to its original after original shape after the force has been removed. Like for example, if you have this bended nails here, so this is actually already what happened is when you can see deformed shape like this materials has undergone plastic deformation. So this deformation is permanent. So plastic deformation occurs when atomic bonding are stretched beyond the ability to return. So let's look at this piece of metal again. If I put just a little bit of force, you can see that it's become springy, but it does not change shape. So what happened there is elastic deformation. But when I put the force too much to that piece of wire, what is happening that it can no longer go back to its original position. So during this time, I put too much force that I have now stretched the atomic bonding between the atoms inside the crystal structure. So it's too much, they cannot go back to their original position. So during this deformation, planes of atoms slide past each other. So as you can see in this diagram, so what I did just then was exactly this thing. So I stretched them too much, and these atoms in this region here is now cannot go back. The bond between the atoms in that region has now being disrupted. So the atoms move and bonds are broken, but because of the metallic bonding, new bonding will be reformed. So instead of as what I have explained with ionic bonding is when you move them, because of the two similar ion is going to now interact with each other, they're going to repulse and it's going to shatter. With metallic bonding, because of the similarity of the atoms in the entire volume of the materials, as soon as the bonds are broken, new bonds will be reformed. But this definition of plastic deformation is oversimplified. So now from that definition that I gave you, you probably will think if I have this series of atoms and you have a lot of this series parallel to each other, okay? If I can move and break the bond inside these planes, I can deform this material plastically. But it's not that simple. So for example, to actually break that bond between this plane, inside this plane, it requires a lot more force, a lot more stress to break this whole plane of bones here. But the yield stress of materials is actually much lower than this stress that requires to break this bond. So for example, steel. So steel materials has a yield stress of around 350 megapascal. So I can tell you to actually break the whole series of atoms, the plane, to actually break a whole plane of bones, it requires a lot more than 300 megapascal. So what actually happened there? So there must be something else happening here that allow this metal to be deformed at a much lower stress. So deformation is actually corresponds to the motion of large number of dislocation. So remember when we talk about defects, when we talk about line defect, such as edge dislocation. So edge dislocation is, if you want to imagine them, is we have additional extra half plane. So we have line dislocation, edge dislocation that can move in the crystal structure. So that is what actually happened. When we have a lot of edge dislocation, it is easier for the bone to be broken and to reform again. So that's why it requires a lot less energy than what theoretically the stress that required to break a whole perfect plane. So now we only have half plane, and this half plane, it's easier for us to break the bone and to form a new bone. So that is what actually happened during plastic deformation, and this is what this whole lesson is all about. So this process of plastic deformation produced by this large number of dislocation movement is what we call a slip. So crystallographic plane along which the dislocation travel is what we call a slip plane. So I have given you an example. If I have to choose between two paths to walk, one path has a lot of stones which make them much smoother, and the other path has a lot less stone. It will require you a lot more effort to walk on the path that has a lot less stone, because it is not as smooth as when you have a lot more stone on that path. So the same with dislocation line. They will choose a plane that have a lot more atoms on that plane to travel, because it will require less effort for that dislocation line to move. And this crystallographic plane where they travel during slip is what we call a slip plane. And different crystal structure will have different slip plane where this dislocation line can travel. And I will explore that in this topic, in this module. So plastic deformation corresponds to the permanent deformation that results from dislocation motion in response to an applied shear stress. So since dislocation motion preferred certain planes and direction to travel, I will begin this dislocation motion topic by talking about slip system. So the preferred plane where dislocation motion happen is always the densely packed planes. So we have learned about plane and direction and how we can index them with Miller indices. And if you look at FCC, for instance, different planes in the unit cell will have a different atomic packing. So dislocation motion will always prefer to travel on the plane where it is densely packed. And it will also prefer to travel always where the atoms are touching, in a direction where atoms are touching each other. So in a way, in that direction, atoms are densely packed in that direction. So in the different plane, we have different direction. So the dislocation line will prefer to move in a direction where the atoms are touching one another. Again, because it requires a lot less effort to move on a smoother direction if we compare to a direction where it is not densely packed. So a slip system is a combination of slip plane and slip direction. So the different metal, the different crystal structure, so will have a different number of slip system. So metal with higher number of slip system is a ductile metal. This is because the dislocation can move, or the motion of dislocation can happen in a lot of slip system. So that metal has a lot of has higher deformability compared to the crystal structure that has a lot less number of slip system in its unit cell. So between the three crystal structure of metal, which is FCC, BCC, and HCP, FCC has the highest number of slip system, followed by BCC and HCP. Therefore, the ductility of FCC is far higher. They are more they have higher deformability if we compare to BCC and also HCP. HCP has the lowest number of slip system, so this metal is more brittle if we compare to the other two types of crystal structure. So for FCC slip system, so in FCC crystal structure, there are 4 densely packed planes. So if I bring back the unit cell of FCC, so this is the unit cell of FCC. All these 4 planes are densely packed. So they all, if you compare to the other planes in this unit cell, these 4 planes has the highest number of atomic packing. So the dislocation will prefer to move on this plane. And there are 3 slip directions in each of this plane. These 3 slip direction is where the atoms are touching one another. So this is one direction, and this is the other one, and this is the other one. So all of this direction, you can see that these atoms are touching each other. Remember, the atoms are densely packed. So in that direction, what happened is actually the atoms are actually touching each other. So dislocation line will prefer to move on that plane, either on this direction, that direction, or that direction. So they won't choose this direction here because the atoms are not densely packed in that direction. So they have 4 densely packed planes, and they have, in each plane there are 3 slip direction in which the atoms are touching one another. So FCC has in total 12 slip system. So one example of FCC crystal structure metal is copper. So copper is can easily be shaped even in when it is in solid phase. This is because if there's a lot of dislocation in that piece of metal, when you deform them, when you shape them or process them to induce plastic deformation, the dislocation can happen in this 12 slip system. So they're not restricted to only 3 or to only 6. They can travel in this 12 slip system. So they are more ductile than the other 2 that I will explain following this slide. So for BCC crystal structure, it has 6 densely packed planes. So if I bring back the unit cell of BCC, so these 6 planes are all densely packed if we compare to the other planes on this crystal structure. You're not comparing to FCC, we're just comparing to the other planes in this unit cell. So these blue color planes are all densely packed if we compare to the other planes in this unit cell. So the dislocation line will prefer to move on this plane, but in which direction? So they will prefer to move in the direction with atoms touching one another. So they will prefer to move in that one direction, and also that's the second direction that will prefer to move. So in total, BCC has also has a total of 12 systems. So if we compare to FCC, they both has the same number of slip system. But as I said earlier, FCC is more ductile if we compare to BCC. So they have the same number of slip system, but BCC is less ductile. Now we want to know why. So the reason behind this is if we look at the both close pack plane of these 2 crystal structure, so you can compare the FCC close pack plane and the BCC close pack plane, which I indicate as the yellow color here. So the slip planes in FCC crystal structure are closest packed if we compare to BCC. So close packed plane, as I mentioned so many times, allow the motion of dislocation at lower energy. So that is why FCC, even though they both has the same slip system, FCC metal is more ductile if we compare to the BCC metal. And finally, we have the other crystal structure, which is the hexagonal close pack. So HCP crystal structure has only one densely packed plane, as indicated in this figure here. And there are three slip directions with atoms touching one another. So we have one direction there, the second direction, and this is the third direction. So in total, HCP has a total of 3 slip systems. So HCP, if we compare to the other two metal, has a lot less slip system, and therefore they are less ductile. Metal with this crystal structure are less ductile if we compare to FCC and also BCC. So now that we have talked about the preferred direction and plane where dislocation will prefer to move, we can talk about the interaction between dislocations. So far, when we talk about dislocation, we only talk about one dislocation line and how this dislocation line is going to move on that plane there. But in a crystal, polycrystalline or single crystalline materials, there will be a lot of dislocation in just one grains. So this defect can be introduced during solidification process or during the shaping of these materials. So it can exist in just one small grain. There probably will be hundreds of dislocation, or if not more than that. So dislocation can move through crystal grains and interact with one another. So the strain field around dislocation will cause them to interact or exert force on each other. So if I bring back the schematic of edge dislocation, so we said that edge dislocation is a defect that has been introduced by an introduction of this extra half plane to an otherwise a perfect crystals. So with this introduction of this half plane, the atoms directly above this dislocation line will experience compressive strain, and the one that is located directly below that dislocation line will experience tensile strain. And you can see some of these lattice also experience shear strain. So the introduction of this extra half plane will introduce compressive, tensile, and shear strain to this crystal structure. And for screw dislocation, only shear strain will be introduced. And due to this distortion in this crystal structure that caused by this introduction of these defects, the dislocation will interact between each other in a certain way. So if, let's say, I have two dislocations travel along the same slip plane, and both of these extra half plane that has been introduced is on the top part of that extra half plane. When they meet each other, how will they interact with each other? So that's the schematic, the one on top here. So I'm talking about when the two dislocation is on the same plane and both of this extra half plane is on the top part of that. It could be both on the top part or both at the bottom part. So they're both having what we say as the same sign. So what will happen when they interact is a larger combined stress field is if we compare to a single dislocation will happen. So there will be an overlap of a region of compressive or tensile stresses from the two dislocation. So therefore, an increase in energy of the whole configuration, and the repulsion between the dislocation, these two dislocation will eventually repulse each other. And what happens if, let's say, I have the two dislocation, both travel on the same plane, but the extra half plane, one is on top and the other one is at the bottom. So I'm going to say that they're both having a different sign. So what will happen when they interact is a lower combined stress if we compare to a single crystal, a single dislocation. So when they overlap, the region of the compressive stress from one dislocation with the region of tensile stress from the other dislocation will overlap. So there will be an attraction between this dislocation, and eventually a single perfect crystals will crystal plane will happen. So we highlight there will be a dislocation annihilation happening when the two different sign of dislocation meet each other. So that is how two or more dislocation interact with each other. I'm going to show you a demonstration of dislocation motion using a video of bubble wrap. So this still image here is a still photograph of a bubble wrap. So the bubble have been arranged approximately into a single crystal, and the crystal here, it looks like it's been arranged to HCP crystal structure. So this is HCP single crystal, and we can see there's a few defects here. We have point defect, which is vacancy, and we also have a dislocation defect here. So this is an H dislocation, which is an extra half plane here. So in the next two videos, you will see when there's a few of this dislocation, what is going to happen, how they're going to interact with each other, one thing, and you will see how they only prefer to move in a certain plane and in a certain direction. So the first video that I'm going to show is the video of bubble wrap undergoing compressive and tensile deformation. So it may help you to watch each of these videos several times. So you can see the motion of dislocation through this demonstration. So I'm going to upload this video in your e-learning so that you can watch it over and over again to grasp the concept on how this dislocation move on a crystallographic plane. So this bubble wrap is undergoing compressive and tensile deformation. So you can see the movement of dislocation during this plastic deformation. So that's compressive, and now I'm going to show you when this bubble wrap undergoing shear stress. So you can see the dislocation, how it moves in a certain preferred direction and also plane. So at small strain from this video, you can see the arrangement of the bubbles does not change. So this is elastic deformation of the raft. So the bubble change shape and move slightly apart in an effort to maintain the lowest energy closed pack configuration. At larger strain, plastic deformation occur. The bubble raft arranged by dislocation motion. So you probably also notice how dislocation motion occur along 3 directions in this graph. So these are the close packed direction along which the distance between the bubble center is the smallest. So dislocation motion along a crystallographic direction is what we call as a slip. So dislocation motion occur by consecutive bone breakage, and this is how plastic deformation happen. So by moving one step to another, one unit cell to another unit cell, it requires a lot less stress than trying to move a whole plane of atom past one another. So this is why at the very beginning I told you that plastic deformation happen at a much lower stress than what it would be required to move a whole plane of atom past another. So this is through dislocation slips. So when a single crystal is deformed under tensile stress, it is observed that the plastic deformation occur by slip on a well-defined parallel planes. That is why we said that single crystal material is an isotropic material. So this material has a properties that is dependent on its direction. So at a different direction, we will get different properties of these materials because the slip only happen in a well-defined crystal planes. So this video here shows a single cadmium crystal undergoing deformation in an scanning electron microscope. So you can see the appearance of slip steps as slip begin on a previously undeformed crystal. And you can see that these steps are parallel to each other. So this is how the formation or plastic deformation happen in a single crystal. So basically, after the atomic block have emerged from the material by one or more atomic distance, they are visible under microscope as slip steps. So when you look at the microscope, you can see the plastic deformation. So the formation of step on the surface of single crystal by the motion of edge dislocation is schematically represented in picture A here, and by screw dislocation is schematically represented by image B here. So now that we understand how the slip step happen in the single crystal, we can now look into the polycrystalline material. So with polycrystalline materials, in general, metal do not have a uniform lattice orientation. It has a crystal structure, but what would happen is during solidification, we will have grains, formation of grains in different region of the volume. So each of these grain has its own different lattice orientation. So you can imagine that each of these grain, you can imagine it as a single crystal, but they are in one volume. So one grain has one direction, one grain has one direction. So they're all having different direction. But you can imagine that one of these grain act as a single crystal and the other as another single crystal, and they all combine together. So in polycrystalline material, several slip systems with different slip plane and orientation are always simultaneously activated. So when we put tensile stress, we apply tensile force, what's going to happen, all of this slip plane orientation will be activated simultaneously. That is why polycrystalline material, we classify them as isotropic materials, because in each direction, the properties of each direction, we will assume that is all going to be the same, because of this different orientation of these grains. So apart from deformation by slipping, plastic deformation can also happen by twinning. So in slipping, sliding of plane between row of atoms happen. So in deformation by twinning, one or more row of atoms may be displaced laterally along the glide planes, or what we call as twinning glide, where a small displacement is taken up by each row within the lattice. So crystal twinning occurs when two separate crystals share some of the same crystal lattice point in a symmetrical manner. So atom movements are much less than by slipping. So it occurs in metals that having less number of slip system. So in a metal usually with HCP crystal structure. And this type of deformation happen at lower temperature. So to conclude, from this topic, we have learned that elastic deformation is a temporary deformation and plastic deformation is a permanent deformation caused by dislocation motion. And different type of metallic crystal structure has different number of slip system, and metal with FCC crystal structure has the highest number of slip system, making them more ductile than metals with the other crystal structure. And apart from slip, metal can also deform by twinning. Alright, so that's about it for this topic. I will see you in the next video where I will talk about how to strengthen metallic materials. Thank you very much.